Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're going to go over how to figure out what the partial pressures are of gases as well as the moles at equilibrium for a given reaction. So let's get into this. So in this problem we're told that the equilibrium constant for the reaction below at 986 degrees Celsius is 0.63. A mixture of 1.0 mole of water vapor and 3.0 moles of carbon monoxide is allowed to come to equilibrium at a total pressure of 2.0 atmospheres. And then they give us this balanced equation. Carbon monoxide gas reacts with water vapor to form carbon dioxide gas and hydrogen gas, and this is an equilibrium. And we have two questions to answer. The first one is how many moles of H2 are present at equilibrium? And the second one is what is the partial pressure of each gas at equilibrium? So let's get into this. So first we're going to find how many moles of H2 are present in equilibrium. So what we need to do is do an ice table first to find out what the equilibrium expressions are. And so we'll start there. And so if we look at the 0.63, that tells us that the equilibrium is close to 1. One side is not really more favored than the other. This also tells us that if we compare the K value of this reaction to the molarities or the concentrations, they're very close together. So that means that we're not going to be able to assume or that X is small, because if you look at the moles, and again, they're not giving us any volumes here, they just give us moles. So when it comes to molarity, remember when you do your ice table, you have to have molarities. Well, in this case, since the reaction is under the same temperature, and we can assume that it's going to also be in the same volume, same container, and we don't know what the volume is, we can pretty sure pick any volume. So we could just pick 1 liter. And so we can go ahead and just use the moles as if they're the same as molarity. And if you see that the starting values, 3.0 moles, and where's the other one? 1.0 mole. That's really close to 0.63. In order for X to be small enough to be negligible, you would have to have an order of magnitude, at least an order of magnitude of difference between your K value and your molarity, 1 and 3. Though the difference would have to be on the magnitude or on the order of 100 or even 1,000 difference. And that's not here. They're not even on a magnitude difference. They're not even on an order of difference of like 10. So so the X is small approximation is not going to be valid in this case. So we have to do an ice table, and then we have to do the quadratic formula. So let's go ahead and get started. So I'm going to do my ice table down here. So here's my ice table. We start off with 3.0 moles of CO. So I'm going to write here 3.0. And again, we're treating moles the same as molarity. And for the water vapor, we have 1.0. And then for the carbon dioxide and hydrogen, we're going to start off with 0 there. And since we have 0, it's going to shift in this direction to make product, since we don't have any product. So we're going to lose an X amount here and here. And we're going to gain an X amount here and here. And they're all X's because we have to pay attention to the stoichiometry of the balanced equation, and the balanced equation is 1 to 1 to 1 to 1. So we're going to lose an x amount on this side, 1 to 1, and we're going to gain an x amount here, 1 to 1. Okay? And now we just add these together to get our equilibrium expressions in terms of x. So here we're going to have 3.0 minus x. Here we're going to have 1.0 minus x. And again, here we're just going to have x and x. All right, so now we go ahead and put this into our k expression, our equilibrium constant expression. So if we write that out, it's going to be Kc is going to be equal to products over reactants. So it's going to be the concentration of CO2 multiplied by the concentration of H2 over the concentration of the reactants. So the concentration of CO multiplied by the concentration of H2O. And all of them are in the equilibrium constant expression because they're all gases. Water is a gas, so that would go into the expression as well. And because the coefficients are all 1, then the powers are all 1 there. Okay, so now that we have that, we can put these expressions in, put the x expression. So that means that the CO2 is x, the H is x, so it's going to be x times x divided by, and then we have CO as 3.0 minus x, so we're going to put 3.0 minus x times, and then we have the water concentration, water vapor, and so that's 1.0 minus x, so we're going to put 1.0 minus x. And all of this is equal to the Kc value that we're given, 0.63, so we'll put that in, 0.63. And so now at this point, it's solving for the quadratic equation. So let's go ahead and do that. So stay tuned. Okay, welcome back. So I moved the equation over here. So I have it over here. I move it over here so I can do some more work. So we're going to have to undo this mess. Well, not really a mess, but we got to write this in a form of a quadratic equation. And so what we're going to need to do is we're going to have to unfoil this and multiply this together. So what we're going to get is we're going to get x squared. And then when we unfoil that, we end up with, let me look, 3 minus 4x. And then plus x squared. Okay, so then we have this is equal to this. And then what we're going to have to do is multiply this on both sides to get it over here. So we're going to have 0.63 multiplied by this, 3 minus 4x plus x squared. And that's going to be equal to x squared. Okay, so now we have it in this form, and so now we're going to have to multiply the 0.63 through, and when we do that, we get 1.89 minus 2.52 x, and then we get 0.63, so plus 0.63 x squared, and that's equal to x squared. And then the final thing we need to do is subtract x squared here from both sides. So minus 1x squared minus 1x squared. And then finally we get 1.89 minus 2.52x. And then this is going to be minus 0.37. So 0.37x squared is equal to 0. So here we have our quadratic equation. And so now we need to put this into the quadratic formula. So stay tuned for that. Okay, so here I have the quadratic formula. And just to review, we have B, A, C. And so this, this number here in front of the x squared, that's our A. And then this number here, the coefficient in front of this x is B, and then this is C. So this is going to be A, B, and C. So we plug these values into the equation, and we'll get two values of x. So x is going to be equal to minus B. B is already negative 2.25. So it's going to be minus negative 2.25 plus or minus, and then it's the square root of B squared. So B is, again, negative 2.52. So we're going to have negative 2.52 squared minus A times C. A is negative 0.37. So let's extend this. So it's going to be minus 0.37 multiplied by C. And C is the 1.89 here. So let's extend this a little bit more. Am I still on the screen? Yes, I am. So 1.89, 1.89. And then we're going to divide all of this by 2a. So 2 times a. And again, a is negative 0.37. So we're going to put that here, negative 0.37. So 0.37. And so now we have everything plugged in. Oops, I forgot. I almost made a silly mistake here. I forgot the 4 in my formula. I forgot that 4 there. So that's going to be 4 times a, negative 0.37 times, and then we have C, 1.89, 1.89. Okay, so now that we have everything plugged in, all we have to do is multiply and divide and all of that. And so I'm not going to follow each step. So when you do the multiplication and division and all that, you're going to get x is equal to negative 3.405, negative 3.405, plus or minus 4.087, 4.087. Let me double check that. Negative 3.405 and plus or minus 4.07. Yeah, 87. Okay, so now what I need to do is I'm going to get two x values. So the reason for the two x values is because if I add 4.087 to this, I'll get one x value. and then I'll subtract 4.087, and I'll get another x value. And so let's do that. So one x value will be 0.682, or the other x value is going to be negative 7.492. Negative 7.492. So here's the two possible x values from our quadratic formula. And you'll see that the negative one is not going to be allowed because x, we're talking about x here. And our x value, if you remember from our ICE table, x is the amount that's being changed, and you can't have a negative amount, so that's not going to be the right answer. So here is our x value here. So now what we can do is use that x value and plug it into our original expressions for the equilibrium concentrations. So let's go back to that. Okay, so here we are with our equilibrium expressions in terms of x. If you remember, the concentration of CO at equilibrium was 3.0 minus x. The water vapor concentration at equilibrium was 1.0 minus x. And the concentration of CO2 is equal to the concentration of H2, which both of them were equal to x. We now have our x value, so now we can plug that in. So then we have 3.0 minus 0.682, which is going to give us 2.318 moles. And these are moles, right? Because remember, concentration and moles were treated the same in this problem because we weren't given enough volume, so we just assume any volume, it's got to be the same volume, so therefore why not one liter? So this is the number of moles of CO at equilibrium, and we do the same thing here, 1.0 minus 0.682, and that's going to be equal to 0.318 moles of the water vapor, and then both of these are equal to x, which of course is equal to 0.682 moles. So we now have the answer to the first question, how many moles of H2 are present at equilibrium, and our answer is 0.682 moles. Now we can go to the next question, which is what is the partial pressure of each gas at equilibrium? And so this is where the moles are going to come in, because we're going to have to use the mole fraction to help us do that. And that's why you've been probably wondering, Mr. Koval, are you going to use this 2.0 atmospheres that they gave us? Why, yes. Thanks for asking. That is a great question. Yes, we're going to use the 2.0 atmospheres. So the equation that we want to keep in mind is that the partial pressure of a gas, so partial pressure of gas A is going to be equal to the mole fraction of A multiplied by the total pressure, right? So they gave us the total pressure, 2 atmospheres. So to find the partial pressure, all we have to do is find the mole fraction, multiply it by the total pressure, and we get the partial pressure of each gas. Well, how do we find the mole fraction? Well, the mole fraction is simple. The mole fraction, as the name indicates, is a fractional representation of the part over the whole, right? So whenever you have a fractional amount of something, you're looking at the moles, or the part of something versus a whole. Here we're looking at the mole fraction. So the mole fraction of a particular gas is going to be the moles of gas. So if this is the mole fraction of gas A, then we're going to compare the moles of A to the total moles. That's our mole fraction. So if we're going to get a percent mole or a molar percentage, then you would just multiply that by 100 to get the percentage. But we just want the mole fraction. So to calculate the mole fraction, all we need to do is take the mole amounts. So for example, for CO, carbon monoxide, we know that we have 2.31 8 moles. We need to get the total here. So if we add 2.318 plus 0.318 plus, and then we have twice this, so we have 2 times 0.682. If you add all of this together, you get exactly 4 moles. So 4 moles is the total. So now all we need to do is, I'm going to go ahead and erase this here. We don't need that anymore. And so now I'm going to say, okay, the partial pressure of CO, so we'll start with this one, is going to be equal to the mole fraction of CO multiplied by the total pressure. Okay, that's what I have there. And so now I'm going to take the mole fraction. So this one's going to be, again, the partial pressure of CO is equal to the mole fraction, which is the moles of CO, which is right here. So we're going to take 2.318 divided by the total moles, which we said it was 4. So 4.000. We multiply that by the total pressure, which is 2 atmospheres. Where to go? 2 atmospheres. And that's going to be equal to, when we calculate that, that's going to be 1.159. 1.159 atmospheres. So that's the partial pressure of CO. Now we can do the same thing with water vapor. So the partial pressure of water vapor is going to be equal to the mole fraction of water vapor. And so we're going to take the moles of water vapor, 0.318, 0.318, divide that by the total moles, which is again 4.000 moles. And we're going to multiply that by the total pressure again, 2.0 atmospheres. And then we're going to calculate that, and we get 0.159, 0.159 atmospheres. So that's the atmospheres of water. And then since the carbon dioxide and hydrogen gas are the same, we can do the same one calculation for that. So the partial pressure of CO2 is going to be equal to the mole fraction of CO2. So we're going to take the 0.682, 0.682 moles divided by the total moles, which is 4.000, multiply that by 2.00 atmospheres, and you get 0.341, 0.341 atmospheres. And since this is the partial pressure of carbon dioxide based on the moles of carbon dioxide, the moles of H2 are the same, so the partial pressure is going to be the same as well. So this is also equal to the partial pressure of H2. And there, ladies and gentlemen, is how you do this type of problem. I hope this is helpful. If you enjoyed this video, if this helped you in any way, then by all means, please like the video, share the video with your friends and family and loved ones, and also make sure you hit that like button for real, and subscribe to my channel, hit that notification bell up there, and when you do, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great one.